Hello, everyone. Welcome to study the heat transfer and ocean floor topography. I'm Yan. Today, I'm going to talk about the heat flow, the temperature distribution in the interior of Earth. So the outline of today's lecture will be first, I'm going to talk why do we study heat flow. And then I will introduce an important law that is Fourier's law for heat conduction and how we can use that law to measure the Earth's surface heat flux. Then I will introduce some heat generated by the decay of the radioactive element. And then one-dimensional time-dependent heat conduction, what is the fact of time? And use that to calculate the isotherm of the oceanic lithosphere and how the ocean floor topography will evolve due to the heat conduction. Why do we study heat flow? Since the solid part of Earth like mantle and crust, their reality is dependent on temperature. For example, at the surface, the crust behaves like an elastical material, which is when you have a force, it will deform. When you remove the force, it will recover. However, in deeper mantle, in a very long time scale, it behaves like a flow, like water. So to understand the thermal structure of the Earth, it's important for us to understand the geodynamics of Earth. There are three ways for heat transfer. The first is heat conduction. It's by the collision of those small molecules. So in the part with higher temperature, those molecules have higher kinetic energy. And by the collection of those molecules with the molecule with lower kinetic energy, the energy can transfer from this hot part to the cold part. And for the heat convection, actually the medium itself is moving. So the mixing of the medium with different temperature create heat convection. And finally, heat radiation is due to the transport of those electromagnetic waves. So it don't need any medium since the electromagnetic wave can radiate through vacuum. So we use Fourier's law of heat conduction to describe the heat flux with the relationship of the temperature distribution. The heat flux Q, which is the float of the energy per unit area and per unit time. So at this point, this flux Q is proportional to the temperature gradient at this point. We can see here Q equals to negative K multiplied by the temperature gradient. K is a positive coefficient, which is the thermal conductivity. Pay attention to there is a negative sign here, since from hot to cold end, the temperature is decreased. So the temperature gradient actually is negative. And multiplied by this negative, it will give us a positive heat flux. That means when the temperature decreases from the hot end to the cold end, we actually get some heat from the cooling of this slab. One big question in Earth science is how we can measure the heat flux of Earth's surface. So here is a well which drill into the ground, and we can measure the temperature of different depths. Since we cannot directly measure the heat flux, but we can infer that from the temperature. Since we know if we already know the thermal conductivity K in the layer of the rock, we can use that to calculate the heat flux through this layer by this Fourier's law equation. So we can calculate the temperature difference between these layers, there's delta T, and also the thickness of this slab. And use that, we can calculate Q. So here is one exercise. We know there is at different depths, the temperature is measured by this temperature sensor. And we already know in different layers what is the thickness of the rock and what is the thermal conductivity of that rock. So here, let us just calculate the heat flux through different layers, and also to determine the average heat flux through all those layers. So here's the answer. I'm using Python code to calculate all these heat flux from different layers. And the average value is about 0.081 watt per meter square. Here is a map of global surface heat flux. We can see there are two places where we have higher surface heat flux. One is the mid-ocean ridge, the other is the volcanic arcs. Here is some number of average value of the surface heat flux from continent, ocean. We can see ocean has a little bit higher surface heat flux. And the average value of the surface heat flux of the Earth is about 87 milliwatt per meter square. If there is no heat is generated or absorbed inside the slab, the heat flux Q is proportional to the temperature gradient. However, for most of the rock, there are some radioactive element in it. And the decay of those elements will generate heat. This table is showing for different radioactive element, it has different heat production rate, and also with different decay characteristic time, which is the half-life time. So to calculate the total heat production rate in the present day, we need to sum up those heat generation rate for each element with their concentration. So that means element with higher concentration will contribute more on this total heat generation rate. If we want to calculate the heat generation rate in the past, we also need to consider their decay, since those elements has higher concentration in the past. This is a plot showing the heat production rate as a function of time. 0 is present day, and this is the birth of the Earth. We can see that with the decay of those radioactive elements, the concentration of this element decrease, and also the heat generation rate decrease as well. So potassium and like uranium, it's used to be a main contributor of the heat production rate. However, with the decay of the potassium, now the concentration of the potassium is pretty low. So now the main contributor of this heat production rate is uranium and thorium. Now we need to consider the contribution of the heat production due to those radioactive elements. So the heat production from the zinc slab can be expressed by the heat generation rate multiplied by the mass. And with the density multiplied by volume equals mass, we can actually get this equation. And by the energy conservation, we also can get the energy generated within the zinc slab should also equals to the difference between the energy in and out. Therefore, the difference between the heat flux between these two surfaces should equal to H multiplied by rho and delta Y, which is the heat generation rate multiplied by the density and the thickness of the slab. Here's one exercise. Let's calculate the contribution of heat production in oceanic crust to the surface heat flow. Let's record The difference of the heat flux between the surface and the bottom can be calculated by the heat generation rate H multiplied by the density and the thickness. Here's some value for the oceanic crust. Let's assume the crust has an average thickness of 6 kilometers. So what is the Q? So here is the result, which is 0.45 milliwatt per meter square. Compared to the total volume of the oceanic surface heat flow, which is 100 milliwatt per meter square. It's negligible. That means the radioactive element has little effect on the total heat flux. So if we consider the convective heat transfer in the mantle, the temperature profile will be very different from the only convection is considered. And we can see here the temperature profile, a large part of the mantle has little variation of the temperature. That is due to the heat transfer is dominated by the convection. Actually, the material with high temperature directly move shallower to the surface without changing their temperature a lot. This process, which is called adiabatic process, which means those elements with this temperature going to the surface without losing any heat. The temperature change is only due to their volume change. We can also see at the surface and the bottom of the mantle, the temperature change dramatically. So those layers are dominated by the heat conduction. Since among those places, which is the bottom and the surface, the material is mainly moving laterally. So the heat conduction plays a dominant role. We call those layers the thermal boundary layers. In those layers, we only consider the effect of heat conduction, and we can neglect the heat convection. So in the following lectures, I will introduce mainly focusing on this top layers, which are the thermal boundary layers, where the heat conduction is the dominant effect. So why we are going to study the effect of the time on the heat conduction? Since many important geological process is involving the heat conduction evolution, like the cooling of the oceanic lithosphere during the seafloor spreading, and also including the cooling of the intrusive igneous bodies like dike or plutons. And also there's the thermal effect is very important within the erosion and the sedimentation of the surface process of the Earth. So now let's derive the time-dependent heat conduction equation from the Singh slab. So we want to know what is the energy we need to heat the Singh slab up at a given time. So in detail, first, the heat capacity, which is a constant of the given material. It describes the energy required to rise the temperature of a unit mass of material by 1 degree. So therefore, we can derive for this slab with the thickness of delta y, and the cross section has an area of 1, which is a unit area. So the energy required to heat this slab up by 1 degree at a given time can be expressed by this equation, which is heat capacity multiplied by density and the temperature changing rate and the thickness of this slab. To maintain the temperature change at a rate of this value, we need the difference of the heat flux from this surface to the other equals to the energy required to make this Singh slab has a temperature change in a given time. So with this equation, and since we can know the difference of the heat flux will equal to the second derivative of the temperature on the distance, so we can get this equation. This is the time-dependent heat conduction equation. So this describes the temperature change rate is proportional to the second derivative of temperature on distance. We can further move those constants related to the material to one side and simplify this equation by defining a thermal diffusivity kappa, which is K, the thermal conductivity divided by the density and special heat capacity. Then we get this temperature rate equals to the thermal diffusivity multiplied by this term. So it's a very important feature that our thermal diffusivity kappa has a unit of length square divided by time, such as the square meters per second. So it's a very important feature because if we assume the temperature change occur in some given time, tau, so this feature, the temperature change, will propagate to some distance, and the distance is on the order of the square root of kappa multiplied tau. So similarly, we can also see if some temperature change is propagated to a distance L, we need that much time to make that change. Here is one exercise for you to understand this important feature. So let's use the relationship of the characteristic time tau, which is equals to the square of the distance divided by the thermal diffusivity kappa, and taking the mantle's thermal diffusivity kappa, which is 1 millimeter square per second. So let's determine the characteristic time for the conductive cooling of the Earth. So here's the answer. The characteristic time is about 1.3 trillion years, which is much greater than the age of the Earth. So that means the heat conduction is very inefficient. Now let's use the time-dependent heat conduction equation to solve our real question for the cooling of the oceanic lithosphere. So here is the mid-ocean ridge. When the oceanic lithosphere are separated from each other, the mantle will upwell to fill this gap. So for simplification, we just neglect the crust since it's very thin. We only consider mantle. And we can see the top of mantle, it has the temperature as the surface, which is 0 degrees. And all the mantle here, since it's from the mantle convection, it has the same temperature, T1. However, when it's moved with the lithosphere away from the ridge axis, it starts to cool down. So the temperature of the lithosphere will decrease. So we want to know the evolution of the temperature profile in the mantle. So we are going to solve this equation in the mantle with the boundary condition like that. So at times equals to 0, the surface has temperature T0, and all the mantle has a temperature T1, which is same as the very deep mantle. With the time larger than 0, now you can see the lithosphere is going to cool down. And for the deeper part of the mantle, it didn't feel any cooling effect since it needed time for this cooling to propagate to the deep. That's why we have a thermal diffusivity defined here. It's a characteristic time for how the mantle can feel that cooling at the surface. So this is the result of this equation with those boundary conditions. And we can see the normalized temperature by the T1 and the T0 is a function of depth. So in detail, it's an arrow function, and in it, it's y divided by 2 multiplied by the square root of kappa times t. So this complementary arrow function can be calculated by computer. So with those equations, we can calculate the heat cooling history of the mantle. Assume the top of mantle, we have a temperature which is 0 degree, and in the very deep of mantle, it has a temperature about 1500 degrees C. And the thermal diffusivity of the mantle is about 1 square millimeters per second. We can see different curves showing the thermal history in different time. After 1 million years cooling, the thermal structure of the mantle doesn't change a lot from its initial condition. That means the thermal conduction is a very inefficient way for heat to last. Now let's explore the thermal structure of oceanic lithosphere in 2 dimensions. So this is a very simple model saying when the lithosphere is cooling, at the same time, this part of the lithosphere is also moving away from the ridge axis. So use the heat conduction model we have done before. We can explore in different time. Here is time equals to 0, 10 million years, 20 million, and 30 million years. When we focusing on one point here with the temperature of 1300 degrees C, we can also see this point is evolving downward. That means more and more mantle is cooling down. So when we make this part of the mantle moving away from the ridge axis, we can substitute the time in this equation actually with the distance, if we assume the lithosphere is moving with a constant speed. So with this equation, we can know the relationship between the depth of certain temperature and the distance to the ridge axis. So if we assume the boundary between lithosphere and asthenosphere is a temperature boundary, actually they are, since the mechanics of those rock is very dependent on the temperature of the rock. So we can calculate the shape of the lithosphere bottom using this equation. Here is one example. If we assume the isotherm between the lithosphere and the asthenosphere is 13 degrees C, and we have mantle thermal diffusivity, and if we assume this ridge is a fast spreading ridge with 80 millimeter per year spreading rate. So here is the result. You can see the lithosphere become thicker and thicker when moving away from the ridge axis. Now I have a question. If we assume this half spreading rate is 20 millimeter per year, what do you expect to see the bottom of the lithosphere? Is that thicker than the fast spreading ridge or thinner? Here is the result. Actually, you have a thicker lithosphere. Since it's moving slow, so it can give the lithosphere more time to cool down. Finally, let's talk about the thermal effect on ocean floor topography. This is the temperature structure of the mantle away from the ridge axis. We know there is a thermal expansion effect on a rock, since when a rock has a higher temperature, it will expand and has lower density. So the cooling of the lithosphere make this part of mantle denser. So here is the density structure calculated by this thermal expansion equation. We can explore different columns of the mantle at different distance to the ridge axis. So actually, the column of mantle far away from the ridge axis will be denser since some part of the mantle is already cooled down and due to the cooling contraction. So with the principle of isostasy, we expect to see those columns of mantle will sink since it's denser. Considering the thermal effect and isostasy, we expect to see the top of the lithosphere is become deeper and deeper when far away from the ridge, since the column is denser due to the thermal contraction. Here is the relationship between the depth of the water as a function of distance if we know the spreading rate. So this is the data we collected at Pacific Ocean. We can see far away from the ridge, it has a deeper and a deeper water. The topography of the seafloor can match pretty good with our model. However, when far away from the ridge, our model overestimated the depth of the water. That means the mantle lithosphere away from the ridge is actually less dense than we thought. The final question I want to think about after class is why does the depth away from the ridge is overestimated by the model? Finally, here is the summary. First, the thermal structure is very important to determine the reality of the Earth's interior. And there is 3 ways of heat transfer: conduction, convection, and radiation. We know the Fourier's law of heat conduction, and we also learned that the radioactive element plays some negligible effect on the total heat flux of the ocean surface. And we also know the concept of the mantle convection and a thermal boundary layer. We also know we can use simple equation to describe the cooling of oceanic lithosphere and what is the thermal effect on the topography of the ocean floor. So that's all for today's lecture. Thank you for watching.